All right, good morning, everyone. So we're going to get started because we've got a little bit to get through before you have your test on Monday, Monday. So let's get into it. We last time talked about balancing equations, and then we looked at the different types of equations. There's one equation that we still need to cover that you need to be able to classify, and that is an oxidation reduction reaction. So when you look at the equipment that's over here on the right, this all has rusted. Rust forms when oxygen in the air reacts with the iron of the material. And what happens is that an electron is actually transferred from one material to another. Specifically, an electron is transferred from the metal to the oxygen, and that's what bonds them together. The transferring of electrons is what indicates that it's oxidation or reduction. So oxidation reduction reactions, some examples, they provide us with energy with food. So when we metabolize food, that's an example of an oxidation reduction. Anytime we have electrical energy in batteries, that's a transfer of electrons. And then rust. Here we have, this arrow should be down here. But this opportunity where we have metal reacting with oxygen to produce a metal oxide is an example of an oxidation reduction reaction. So in an oxidation reduction reaction, an electron is transferred from one thing to another. So here we've got material A and then material B. Material A has an electron that it will transfer over to material B. So our ending result is we still have like A and B, but A is short that electron and B is up an electron. Now, if you're short an electron, what should happen to your charge? If you're short or you lose an electron, you should become more positive, right? So the things that lose the electron will become more positive in charge. The thing that gains the electron will become more negative in charge. So that's one way to indicate whether something is being oxidized or reduced. In this case, the thing that's losing the electron is being oxidized, or that's known as oxidation. The thing that's gaining the electron is known as reduction. And there's a little mnemonic thing that you can use here, which is oil rig. Oil for oxidation is loss. Oxidation is loss of electrons. Rig is reduction is gain of electrons. Okay, so if you have an oxidation reduction reaction, oil will be the oxidation. This thing here is being oxidized. Rig is the thing that's being reduced. This is gaining electrons. These slides get all messed up sometimes. Okay, we're just going to skip that one because that is a total mess. Here, we'll look at this one here. Okay, so if I take a bar of zinc and I put it into a solution of copper sulfate, electrons will transfer from the zinc to the copper. Let's look at this equation down here. So when determining what is being oxidized and what is being reduced, I like to find my partners on both sides. So what are the things that are like almost the same minus like, you know, a couple electrons. So this thing and this thing are the same, right? And then this thing and this thing are talking about the same thing. Now, in order to go from zinc, and anytime zinc is in elemental form like this, or any element is in elemental form, it has a zero charge. All right, so this thing we can assume has a zero charge here. Well, if we go over here to a 2+ charge, what did it have to do to have a 2+ charge? It had to give up 2 electrons, right? So it said bye-bye to 2 electrons. Oil rig. Oxidation is loss. So the zinc is being oxidized here because it's losing electrons. What's happening with the copper here? Copper is a 2+ over here, and here it's a neutral charge. So it had to eat 2 electrons to get to that neutral charge. So this is gaining electrons. Gaining is reduction. So we can say that this thing is being reduced. So really you want to just look at like what's happening with the charges. That will tell you what's going on. If we look at some of these, identify the following as oxidation or reduction. Okay, we've got SN, solid or tin. And then there's an arrow and it says, well, the tin is becoming tin with a 4+ charge and it's kind of pooping out 4 electrons, okay? The plus means that it's separated from this. So what process will you lose 4 electrons? Oil rig. Loss is oxidation. So we can say this first one is being oxidized. Next one here, the iron has a 3+ charge and the electron is on the reactant side. So that means it's eating that electron up. And another way you can see that is here it's a 3+. What happens over here? It's a 2+. So it had to eat an electron or gain an electron. When you gain an electron, you're being reduced. Here, again, anytime you're in elemental form, even if you're as a diatomic, you can assume a 0 charge. Okay, so this thing over here has a 0 charge. This chlorine has a 0 charge. What's happening over here? It has a minus charge. And it's also saying that it had to eat 2 electrons. So if it's gaining electrons, that means it's being reduced. So the first one is an oxidation or a loss of electrons. The bottom 2 are reduction or gain of electrons. So look at this. In this one thing is being oxidized and one thing is being reduced. I want you to tell me which thing is being oxidized and which thing is being reduced. So we've got 2Ag plus 2Cl minus gives me, when I have UV light, 2Ag plus Cl2. Now remember, anytime you are in elemental form like this without the charge, or you're in a diatomic, you can assume a 0 charge for both of these, okay, if it's not written in. All right, so let's pair them up. So this thing and this thing and this thing and this thing. I still use oil rig sometimes, like when my brain's not working, I'm like, wait, which one is the loss of electrons? So I'd write that out whenever you're doing an oxidation reduction. Here, we have a plus charge and we go to a neutral charge. Both of these actually end up going to a neutral charge. But if we are starting positive and we go to neutral, that means that we had to eat an electron, right? Or we had to gain an electron. So this would be reduction. Because if we're positive, we're kind of above the neutral line. I need to have something negative to get me back to the neutral line. What about what's happening over here? I'm starting negative and I want to become a neutral charge. So I have to get rid of some of this negative charge. So I have to get rid of the electron or lose the electron. If we lose the electron, we're being oxidized. Again, you've got to think of the electron as a negatively charged thing, all right? So you're moving around something that has a negative charge. Okay. So this is really going to be the extent of oxidation reduction. It's going to be look at the charge initially, look at the charge at the end, oil rig it. Is it gaining or is it losing in determining which one's oxidized and which one's reduced? That's really it. We're going to kind of blow through this biological system thing right now because we haven't gotten into our bio stuff. It's talking about oxidation and reduction. You can think of oxidation and reduction. Oxidation is a loss of hydrogen, and oxidation is an addition of oxygens. We will talk about this at the end of the semester. I'm not going to test you on that right now, so we'll leave that. Okay, this is the big kind of finale of the chapter because this chapter is just the chapter that keeps giving. So this is all about stoichiometry. It's kind of smushing all the chemical quantity stuff together and reactions together. So let's look at this reaction here. We've got iron plus sulfur will give us iron 3 sulfide. When we balance that out, the balanced equation, which you can write out, is 2 iron plus 3 sulfur will give us Fe2S3. And the coefficients sitting in the front will allow us to preserve the law of conservation of mass, right? So if I have 2 irons at the end here, I've got to have 2 irons in the beginning. If I've got 3 sulfurs, I also have to start with 3 sulfurs in a chemical reaction. So the law of conservation of mass indicates that in an ordinary chemical reaction, matter isn't created or destroyed. There shouldn't be a change in the total mass, and the mass of your products equals the mass of your reactants. So if we threw this, let's look at a different equation here. We've got silver plus sulfur, and then it reacts to form silver sulfide. Silver, we've got a 2 in the front, and then the final is Ag2S. Well, if I was to use my raw materials and measure them before I ran them through the equation, this over here, let's say we have 215.8 grams of this. We've got 32.1 grams of this. My final product is 247.9 grams. So it's really just the 2 of these added up because mass should be the same. Here's all of our different types of chemical reactions, just a reminder. Great. Okay, so this is the important thing. These slides. I'm doing this. Move this over. There we go. Okay, so remember when we were talking about this formula here, and we said that it was a mole relationship. So it's 2 moles of iron for every 3 moles of sulfur. The same thing is true with a balanced chemical equation. The chemical equation is a mole relationship. It's not a mass relationship. It's not saying 2 grams of this and 3 grams of this produce 1 gram of this. It's a mole relationship. So it's saying 2 moles of iron need to combine with 3 moles of sulfur, and it will produce 1 mole of this iron sulfide or iron 3 sulfide. So now we can kind of hop around an equation if it's balanced. If I give you a certain amount of the product, I could say, hey, how much sulfur do I need to produce that specific amount? You can actually move from one thing to another because you know it's mole relationship. You know, if you want to make 1 mole of this, you have to have 3 moles of the sulfur. If you want to make one mole of this, you got to have 2 moles of the iron. So within each chemical reaction or balanced chemical equation, you're going to have all these different conversion factors. And anytime we have conversion factors, we can do dimensional analysis and we can jump around. So we could compare, bothering me. We can compare, if we wanted to, we could compare iron with sulfur. I could compare the 2 reactants. I could say, hey, if I've got a certain amount of this, how much of this do I need to fully react with all of that? I could compare iron to the product. I could compare sulfur to the product. So you have quite a few things built in. But you don't have to write every single one out. Where are these numbers coming from? They're just getting pulled off of the coefficients, right? This 2 and 1 is coming from the 2 here, and then the 1 that's inferred in the front. So they're all built in with the coefficients. Yay. So now we can do stoichiometry. So here it says, consider this following equation. What's a mole to mole ratio of H2 and N2? So if we want to compare H2 and N2, here's H2 and here's N2. Relationships are going to be 3 H2s for every 1 N2. The only one that applies there is this second one here. This first one, it looks like it may be correct, but it's not quite. Do you see what the 3 is sitting with? The 3 is sitting with the N. You don't want to flip coefficients. Always pair the coefficient with the compound you're talking about. So this one doesn't work, and then this has a 2 in it. We don't have a 2 anywhere. A mole ratio between NH3 and H2. So here we're trying to combine NH3 and H2. This relationship is a 2 to 3 relationship, or a 3 to 2. We just want to make sure we put the 2 and the 3 with the right thing. So 3 with the H2 and 2 with the N2 would be the second one here. So those relationships come in handy if I say, hey, I'm going to give you a certain amount of the reactant, and I want to know how much product I could potentially produce. So how many moles of Fe2O3 can form if you have 6 moles of O2? So if I know something about oxygen, specifically that I have 6 moles of it, can I talk about how much product I would have? And I can, because I know the relationship, right? If you have 3 moles of O2, you're always going to produce 2 moles of the product. So you start with your given, which is 6 moles of O2, and you're going to multiply it using dimensional analysis. So all stoichiometry is really dimensional analysis. It's just converting from one compound to another. So in this case, I'm going to put the 3 moles of O2 on the bottom, and I'm going to put the 2 moles of the product on the top, because I'm asking you about the product, right? So the moles of O2 will cancel, and we just multiply by the coefficient ratio. So 6 times 2 divided by 3, it'll say 4 moles of Fe2O3. So if I have 6 moles of oxygen, and in this problem, we're just assuming you have an excess amount of iron, because it doesn't say anything about the iron, so you can kind of ignore the iron. It's saying, hey, you have 6 moles of oxygen. How much of the product could you get? Well, we could technically get 4 moles of the product. So when running through these, for calculating these, state the given and needed quantities, and it can be in either moles or grams. Write a plan to convert. Use the coefficients to write a mole to mole factor or mole to mole conversion factor, and hop from one to the other. And if you need to use molar masses, go from there. So this one, it's gonna drive me crazy. Okay, I want you to do this one. So this is a simple one because it's only in moles. So assume that you have 12 moles of O2. How many moles of iron do you need to react with 12 moles of O2? And the equation is already balanced for you. Okay, so it's giving you something about oxygen. It's asking for something about iron specifically. And what sometimes students will do is they'll see that iron and they automatically jump to the product. Well, this is iron with oxygen. So just make sure you're really identifying where you're starting and where you're ending. So we want to relate oxygen to iron. So we need a relationship between these two, and I've got coefficients. So I know that 3 moles of oxygen, and it is O2, it's the diatomic, that is important. So make sure you're putting what it says, needs 4 moles of iron. And that is how they relate to each other. So we start with our given, 12 moles of oxygen, and we convert. The 3 moles will go on the bottom, 3 moles of O2 will go on the bottom, and the top will need 4 moles of the iron. So you're going to take the 12, multiply it by 4, and divide it by 3 to give us the correct answer. The moles will cancel. So it's similar to what we did earlier in the chapter. This is such a mess. So our ending answer is 16 moles. Now, as always, how often are things given to us in moles in real life? They're not. They're given to us as mass, a mass amount. So if we're doing calculations where we're given a mass and we need to find the mass, there's a flow chart that we want to follow. And this is it. We're going to go grams to moles to moles to grams, grams to moles to moles to grams. So grams of compound A, whatever that is, generic compound A, you will convert it into moles of compound A. And then you'll convert it into moles of compound B. And then you'll convert it into grams of compound B. So if I give you compound A in grams and I want compound B in grams, you have to do 3 hops. There is no way to go directly from grams of A into grams of B. So don't try. All right, you've got to go step by step. So how do we get from grams of A into moles of A? Well, this is always using molar mass, right? Anytime we go from grams to moles or moles to grams, we use molar mass of A. Moles of A to moles of B, this is the mole to mole factor from the balanced equation. So I'm going to add balanced equation there. That's what we just did. That's what you guys just did. You started at a mole value and you went to a mole value. So the thing that's nice about this flow chart is you can kind of pick it up and end where you want. So if the problem is saying, hey, you have this many grams of A and I want moles of B, well, you know you're going to start here and you're going to end here and you don't have to do that last step, right? You guys happen to be starting here and ending here, so you only had to do 1 hop. If we want to go from moles of B into grams of B, this is where we use the molar mass specifically of B. Okay, so molar mass of A is in the A section, molar mass of B is in the B section. How do you get from A to B? That's the magic middle step where you use the coefficients, where you get to transfer from one thing to another. So this flow chart will get you through stoichiometry and limiting reactant problems. Let's do one. Here, so we have 32 grams. Suppose we want to determine the mass in grams of NH3. That can be produced from 32 grams of N2. And here's the following equation. So I'm going to write this over here because okay, so we have an equation where we have N2, it's combining with H2 to produce NH3, 2, 3. Okay, so there's a 1, a 3, and a 2. And we are given that we have 32 grams of the N2. And I want to know potentially how much product we could get. So NH3 in grams, right? How much of that can we have? So we're going from here to here. We don't really have to worry about the hydrogen. We can just assume that this is in excess. If it doesn't tell you it's in excess, or if it doesn't tell you anything about it, you can just assume you have more than enough. So my flow chart for this is compound A. This is what I'm starting with. This is compound B. So I'm going to write out a plan. I'm going to start with grams of N2. And then I'm going to go to moles of N2. Then I'm going to go to moles of my product, which is NH3. Then I'm going to go to grams of NH3. Gram here, gram here, gram here, gram here, but there's a couple steps in between. How do I get from grams of N2 to moles of N2? I have to use the molar mass of N2. Do you see how it's a diatomic? That means you need to take into account 2 nitrogens. So its mass is not, my daughter keeps stealing my periodic chart. I don't know why. She's like messing with me. Okay. The mass is not 14. It's actually 18 because there's 2 of them. It's super common for people to forget that or to miss that. So if you're doing like the homework assignments and it's not working for you, that may be the case. What is this here? Well, this is the magic step that gets us from one thing to another. That's where we use the coefficients. And so 1 mole of N2 will always produce 2 moles of that NH3. Okay, then here we need the molar mass of what compound B is, NH3. So that's 14 plus roughly 3. So it's like 14, 7, it's like 17. I'm going with 17 because I'm being lazy right now. Okay, it's 17 grams. There's a decimal or 2 in there. So when we start moving through, start with your given. So our given is that we have 32 grams of N2. I need to get it into moles. So if I'm getting it into moles, the gram goes on the bottom and the mole goes on the top. 1 mole of N2 is roughly 18 grams. Now, well, we'll keep going there. So I'm going to just thread it together. Yes. What did I put? 18? Let's go with 28, not 18. Thank you. 28. I don't know where the 18 was coming from. So yes, multiplied by 2. So the next step is to get us out of nitrogen and get us into the product, right? So moles of N2 for moles of the product, NH3. We've got to fill in the relationship. So it's a 1 to 2 relationship. Coefficients only get used at this middle step. Okay, this is where coefficients go. You don't add coefficients here. Sometimes people will think, like in this next step, they're like, well, I have 2 moles of it, so don't I want to put a 2 mole here? No, you take that into account in the middle step, you leave it on the edges. On the edges, when you're using molar mass, it's always in relationship to 1. So 1 mole of our NH3 will produce 17 grams of NH3. So we can see here the mass of my compound A cancels, the moles of my compound A cancels, and the moles of my compound B cancel, and I'm just left with grams of compound B. This will be the setup every time you're doing stoichiometry. So we're going to take 32 and multiply it by anything on the top. So we've got times a 2 and times a 17. And then we divide it by anything on the bottom, really just that 28. So we get 30, I got like 38, 39 grams. So if I potentially have 32 grams of N2, I could make 39 grams of NH3. So that is sort of your structure every time you do these. So I want you to work on this one. Here is a balanced equation. How many grams of oxygen are needed to produce 45.8 grams of Fe2O3? So you know something about, you know for sure how much product you want, and it's asking you about a reactant. There's A, B, and C, but I wouldn't even worry about that. Just kind of solve it the way that you had before. So in the beginning here, you might want to start with a flow chart and then fill it in and then solve. I'll give you all, give you about 4 minutes to do that one. Okay, so this one here, we are looking at, we're given grams of this. We want to find grams of this. This we can sort of ignore. I mean, you can't ignore the iron in that like it plays a role in the balanced equation and you would need it to balance the equation. But right now, we're just looking at these two things. So we're going to start with grams of our Fe2O3. We're going to flow that into moles of Fe2O3. Then we're going to move that into moles of oxygen. And then we're going to put that back into grams of oxygen. All right. Filling in the steps here, we need the molar mass of this thing. Here we need the molar mass of oxygen, which it's O2, so it's not 16, it's actually 32. And then in the center, the relationship between these two is, well, 2 moles of Fe2O3 yields 3 moles or needs 3 moles of the oxygen, O2. Okay, so that's our setup. So grams to moles to grams. The molar mass of Fe2O3 is roughly 159.7. Where did that come from? Well, it's 2 irons and 3 oxygens. Here's our relationships. Oxygen O2 is 32. So we string it together, and we want the grams of compound A to cancel, the moles of compound A to cancel, and then the moles of compound B to cancel, and we should be left with just the grams. And here we get 13.8 grams of O2. So the system is, again, the same. First, you're going to use a molar mass to convert into moles. Then you're going to use the coefficient to get into the thing that you want. Then you're going to use molar mass to convert it back into grams. Any questions on this? We'll do one more example problem. If you've taken Chem 092 and you did limiting reactant stuff, we're not going to do limiting reactant in this class. This is going to be the extent of it, okay? So like percent yield, limiting reactant, theoretical yield, all that stuff, we're not going to really be doing that. Astrid, you got 66 for the mass. Did you?
Yeah, I thought it was 3 times 8, which is 24, plus 2 times 26, which is 52. I got.
You're using the atomic number, not the atomic mass.
Oh, so it's
you're telling me how many? Yeah, you're telling me how many protons are in there. But okay. We also want to take into account.
Okay, thanks.
Yeah, cool. Okay, let's do one more, and then we'll call it for this. So the reaction between hydrogen gas and oxygen gas produces 13.1 grams of water. How many grams of oxygen reacted? So here's your balanced equation. This is to produce water. It's pretty easy, actually. You just take some hydrogen gas and oxygen gas, and you can use like a everyday battery, and you can synthesize the water. We have 13.1 grams of water. So I'll give you, I'm just going to give you 3 minutes. Test your skills. Okay, so in this one, we are given something about water and we're trying to find something about O2. We're hopping here. This we can just sort of not think about for right now. So we want grams of water into moles of water, into moles of our oxygen, into grams of oxygen. What is the mass of water? It's roughly 18 grams per mole. What is the relationship between these two? It's 2 moles of water needs 1 mole of this O2. And then what's the mass here? Well, it is 32 grams per mole. Why is it 32? Because it's talking about a diatomic. So just look at it for whatever it says. If it says O2, honor that. So when we plug it in, okay, so we have our 13.1 grams. We're going to divide it by the molar mass to get it into moles. Then we've got our 2-to-1 ratio, and then we multiply it by the molar mass of O2. We should get 11.6 grams of O2. You guys seeing how this is the same thing over and over and over again? It doesn't really matter what the balanced equation is, doesn't matter what's given, you're going to follow that same system. Okay. Question or issue that I tend to see though is people don't even know that they need to do this. They're like, I can do this system, but how do I know that I need to use it? Well, you have to determine that you're running one of these problems. Some indicators, you're given a balanced equation. If there's a balanced equation there, you should probably use it. Another thing, you're given information about one material and it's asking you information about a different material. All right, if it's asking you or it's telling you you have something about water, but it's asking you about O2, that means you have to do some sort of magic transition using a balanced equation. That's all going to lead you to this system of grams to moles to moles to grams. All right, if the problem says something like how many moles of O2 are in 35 grams of O2. Do you need to use this system? No, there's no balanced equation and it's asking you how many moles of O2 are there if you have 35 grams of O2. This is just a simple conversion between grams and moles. Okay, this is oxygen, this is oxygen. It's the same thing. So you don't, sometimes what will happen is students will pull out this to do a really simple problem. In this case, all we're doing is I've got 35 grams of O2. I just want to convert it to moles. So 1 mole of O2 would weigh 32 grams of O2. And those would cancel. That would be the end of the problem. Just a simple one conversion. Okay. So if you're seeing a balanced equation, it's giving you information on one thing, it wants information on another thing, you're going to want to go through this process. Okay. Questions on that process? We're not doing limiting reactant. Okay, so you're not going to have a situation where you're given information on one reactant and another reactant, and you've got to figure out which one limits it. We're not doing percent yield. We're not doing any of that. All right, the last thing that we are going to talk about is energy in a chemical reaction. So thus far, we've kind of only talked about mass in a chemical reaction. Like if I have this much of one thing and this much of another, how much will I get at the end? Well, there's another thing though that happens, and that is energy that's created in a bunch of different ways, heat, light, different sorts of things. Thermite reacts, has a reaction that produces a lot of heat, like a very, very high temperature, so high that it can weld and cut railroad tracks. So when we have a reaction going on, clean this up here. Okay. Reformat these slides. So when you have a reaction, molecules need to collide with each other in order for the reaction to occur, right? If I've got hydrogen and oxygen and I want to make water, well, the hydrogens and the oxygens need to come together in some way to bond. So 3 conditions for a reaction to occur are collision, reactions need to collide, orientation, the reactants must align in the right way to break and form bonds. And then this is energy of activation. So the bonds, or the collisions must provide enough energy or oomph to hit what's known as the energy of activation. And the energy of activation is the amount of energy needed to get the reaction going. And I'll show you a visual of it. So this is the energy of activation, or the activation energy. You can see it kind of looks like a little hump. There's a certain amount of energy you have to put into a reaction in order for you to reach this energy of activation. Once you've reached the energy of activation, then the reaction will just sort of move forward on its own. That energy of activation could be heat, it could be you shaking it, it could be a catalyst, but it's something that's gonna get you to that point. So when we're looking at a reaction, if you have heat release, that's known as an exothermic reaction. The slides are all messed up. There we go. So in an exothermic reaction, heat is released, so you would feel it get warm to the touch. The energy of the products is less than, it's cut off here, but the energy of the products is less than the energy of the reactants. So you start with something that has a high energy, you move over the energy of activation, and then when you get to your products, they're actually a lower energy and heat would be produced. So in this case, this would be an example of an exothermic reaction. Heat is one of the products. So 18 kilocal, remember kilocal or calories or joules, those are all examples of heat or energy. So we had 2 things, they came together and produced methane, and they released heat. An endothermic reaction is going to be the opposite of that. So in an endothermic reaction, heat is absorbed. The energy of the products, so here are my products, this is progress of the reaction, this is energy. The products are over here, they're higher than the reactants. So the reactants have a lower amount of energy. They absorb a lot of energy to get up and over the activation energy, and then we get our products. You'll see in that instance that the heat or energy is on the reactant side as opposed to the product side. You're not producing the energy, you're having to digest or eat the energy. So heat is added to our reactants. So looking at these, and I'll give you arrows in the right spot. I want you to just look at them and tell me if they're exothermic or endothermic. Again, exothermic, exiting, heat is leaving the system. Endothermic, it's eating or digesting or absorbing. So this first one here, just looking at it, I can see this is where the heat is. It's on the product side, so it produced heat. So this thing got warm. This would be an example of an exothermic reaction. The heat is exiting the reactants. This next one here, where is the energy component? It's right here. The energy component is on the reactant side. That means it's being digested or absorbing. This thing is taking this heat to make these products. So this would be endothermic. And then this last one, where is our heat or our energy? Well, it says it there as heat. It doesn't give a discrete number. That's okay. This is very similar to the first one, where the heat is being produced. It's on the product side. So this would be exothermic. The heat is leaving our reactants. So the rate of your reaction, like how quickly these reactants happen, is the speed at which the reactants get used up and the products get produced. There's a couple things that can shift the rate of reaction. One thing, your rate of reaction will increase when the temperature rises. Why? Like, why is it when it's hotter, the reaction tends to go faster? It's because there's more kinetic energy in the molecules or elements, atoms. So they're moving faster, which provides more collision between the molecules. So you can reach that activation energy faster. Another thing that can alter your reaction rate is increases with concentration of your reactants. So if you have more reactant, you have more stuff to play around with. You have more things in there floating around, you will have a faster rate of reaction. You've heard of a catalyst. A catalyst can also increase the rate of reaction. What does a catalyst do? Sometimes people think, oh, a catalyst just pushes the reaction forward. But that's not actually the case. What's happening is that a catalyst will lower the activation energy. So without a catalyst, we can see that the activation energy is all the way up here. So you have to give it enough energy to get to this point, and then the reaction will naturally occur. When you have a catalyst, it lowers the activation energy, so it makes a smaller hump of energy that you have to get up and over to then allow the product to occur. So lowers the activation energy. Catalysts are also not absorbed in a reaction. And we will come back to catalysts later when we get into the biochem part, but you can reuse a catalyst over and over and over and over again. So it doesn't actually get used up or digested by the reactants. It doesn't affect the reactants. It doesn't affect the products as far as like what they're made of or their formulas. It only lowers this activation energy. So couple things, if we increase the reactant concentration, we're going to get more collisions, we'll increase the rate of reaction. If we increase the temperature, we'll get more collisions and more collisions with energy of activation. So more collisions that are meeting that energetic point. And if we add a catalyst, we're going to just lower the whole energy of activation. So I want you to tell me, looking at these, whether this is going to increase the rate of reaction, whether it's going to decrease the rate of reaction, or if it has no effect at all. So if we increase the temperature, we should increase our rate of reaction because we have more collisions. If we remove some of the reactant, okay, if I take some of the reactant out, that means I have less to play around with. I have less collisions. This would lead to less collisions. So this should actually decrease our rate of reaction. You have less stuff to make it happen. Adding a catalyst will always increase the rate of reaction as long as it's the right catalyst. Placing the reaction flask in ice. If I put it in ice, I'm cooling it, I'm lowering the kinetic energy in it. That will definitely decrease the rate of reaction. It'll slow the reaction down. And then increasing the concentration of one of the reactants, that will increase the rate of reaction because you have more things to hit, right? More available opportunities. So increase, decrease, increase, decrease, and then this one got lost, but this would increase it. Yeah. All right, let's look at an actual equation. And I want you to tell me what would be the effect of these things. So looking at this, 2CO plus O2 gives you 2CO2. What would happen to the rate of reaction if we increase the temperature? What would happen if we add O2? What would happen if we add a catalyst? And what would happen if we lower the temperature? Now, most of these are generic. Doesn't really matter what the equation is. This one, B, is specific to the equation. Okay. So in general, if we raise the temperature of any reaction, yes, this reaction and also every other one, it will increase the rate of reaction. This is unique to this specific problem, it says, hey, what if we add O2? Well, you have to determine what O2 is. And that's, in this case, O2 is acting as a reactant. So we're increasing the reactant, so we will increase our rate of reaction. Adding a catalyst in any reaction, as long as it's the right catalyst, will increase our rate of reaction. And then the opposite of A is D. D is lowering the temperature. Anytime we cool something down or lower the temperature, we are going to decrease our rate of reaction. In this case, we don't have any options with no change. So increase for the first three and decrease for the last. So you want to be able to do that, okay? You want to know how those things relate to each other. What would be an example of no change? I'm trying to think. You took the reaction from a table and put it on the floor. You know, you moved it to the floor. You moved its position. You poured it from one container into another container. Will probably not have much of a change. Yeah, things like that aren't affecting temperature, collision, catalyst, concentration. Oh my gosh, and we're done with that chapter. Poof, it's a long chapter, very, very long chapter. So you do have your next test this weekend, or starting this weekend, Sunday and Monday. So you'll want to make sure to do that. Yeah, that's all I've got. I know I had a couple people who had questions on individual things. So you are more than welcome to stay around. Otherwise, I will post these by this afternoon. I've got another lecture I need to do. So I'll post these by this afternoon. If you don't see them by tomorrow, message me and I will make sure they get up there. Otherwise, have a really great weekend. Enjoy some of this awesome weather, and I will see you all on Tuesday. Bye, guys.